All right, so this is section 4B. The title of this is Simple and Compound Interest. Underneath that, it does mention that we want to figure out the difference between APR and APY. APR is the annual percentage rate, and APY is going to be your annual percentage yield. That part actually happens at the very end of the activity, and everything kind of cycles back to that. But just as a heads up, APR, that is the interest rate that would be advertised that you tend to see, and APY, the annual percentage yield, is what actually happens. So interesting thing about this, and a little bit of a preview to everything here, is that actual interest when calculated does not turn out to be the same interest that things are advertised to be. All right, so the first part that we talk about is something called simple interest. And quite frankly, it really is simple. The concept of how this is done is very simple. I mean, the calculations with it are also very simple, but definitely going to be an easier calculation than compound interest. Look, for the most part, simple interest, this is how I describe it to people. That is a type of interest or a loan that you might take from a person that you were very familiar with. So like when you look at these examples, they're going to refer to people's parents or like somebody else who's very close to them. This isn't the type of a loan that you might get from like a bank. All right, so for the first problem, we got Zach, and Zach is, let's see, actually I haven't read the problem recently, I just did the math. He earned $2,000 from mowing lawns, and he's encouraged to save his money. So his father told him that he would pay him 5% interest on the original amount of $2,000 if he would save that, I guess, with the dad. So instead of going to a bank. Anyway, it sets up for a decent problem here. Maybe Zach is a really young kid that did all this. All right, so if the dad says that he's going to pay him 5%, interest on this, the first thing you want to do is find out what is the 5% of the 2,000, and that's just multiplying the decimal form 0.05 times 2,000, which conveniently turns out to be 100, and you might notice that we've done that a lot in these activities. All right, this other little question over here says, what does that really represent? It represents the interest that he's going to get after 1 year. Okay, so $2,000, dad hangs on to it. He gives Zach back an extra $100 for just allowing him to, or teaching him to save, whatever he's doing here. Okay, but if we want to do this for 3 years, the way that the problem is written, what the dad is going to do, he's going to hang on to all that money, and at the end of 1 year, he's going to add $100 onto it, so he actually owes the son $2,100. At the end of 2 years, he would just add on another $100 to the $2,200, and then he would get to, like at the end of 3 years, a total of interest being $300, and then he just adds that onto the 2,000, and that's what he would owe, and you can kind of imagine what it would look like beyond there. That's simple interest. All you do is you take the percentage of what we call the principal balance, what you start with, and that tells you what the increase is going to be every year onto it. All right, so next, we're actually going to start to develop a formula that we can use because, well, you know, what if we want to do a backwards problem? We want to find out, well, how much was invested at the beginning to yield some sort of answer at the end? So we need to know the formulas. Basically, here it gives you all the variables, and you should have already read all this stuff, so I don't need to go through all that. But one very key part to this is that your t that you're going to see later on here, your time is always going to be based on years. And even by the time we get to the end of talking about compound interest, that's also going to be consistent that we measure time in years. That means if you have something like 6 months, 6 months is going to be 0.5. Everything has to be in terms of years. It's an easy fix, but just be aware of it from the get-go here. So if you start talking about months, we got to convert that. All right. All right, how do we end up, like if we took all the numbers that were from above and then we were thinking about how they work together to calculate this, let's look at this part here. So you have the 2,000 and you're adding on the 300. Okay, now the 300 is an actual calculation that stemmed from taking 5% of the 2,000 and then multiplying that 100 by 300. So laid out here, and I guess it's a little bit odd trying to take all those numbers and put into a single like string of like calculation, but it is a good exercise. Okay, so the first blank's the $2,000 that you have. The rest of this ends up being the 300. That part, that's the $100 that we create. So again, kind of weird that you put it in a whole string of like calculations here, because we usually think of it as step by step. That is that first step of figuring out the $100, and then you multiply it by 3 to get a total of 300, which adds on to the 2,000 there. All right, with everything replaced by the variables that they represent, the 2,000s are always going to be P, which is your principal, that's your starting value. The 0.05 is your rate, and then your T here, your time, is going to be the 3 for the 3 years. Okay, so that might look a little bit odd because everything's like spread out. So let me just rewrite what it looks like, sort of condensed down. It's P plus PRT, right? When you see it written all like that, I think it looks a little bit better because you can tell that's a big product, and then it just adds on to the P. Now, you can factor out the principal, and this is going to be important a little bit later on. You actually have two terms here. So imagine everything in parentheses, like that, and both of these terms have a P. So factoring is the opposite of distribution, which I think most people are more familiar with. If you divide the P from each of those and then just move it to the front, you can create this formula, which again looks odd because of all the blanks. But if I condense it down, let's not put an equal there. Let's just say A equals. A equals P, and then in parentheses, you're gonna have a 1 plus RT. Okay, so that P gets removed in the back when it divides out. So there's P out there and you just got the RT. But when you divide the P from this P, you get back 1. By the way, you can always check your factoring with distribution. You should be able to distribute that P back in and get what we used to have there. Well, surprise, surprise, the formulas that we just put together are at the top of the next page here for you. I actually think that's a really clever idea in the activities, to let you do work and then to provide the answers on a different page so you can't see them originally. I do that a lot on worksheets that I write as well. But here they are that we could be able to use. All right, let's see here. Number 5, we go back to Zach. What if he saves for 7 years? Okay, so you should imagine that you'd be adding on $700, right? So there's the 2,000 and then the extra 700 for 100 for every year. Okay, but what we want to be able to do here is get away from the reoccurring calculation, like the repetitiveness of it, and just give a single formula. So this is a great one to use here. That one seems to fit a little bit more in how we process it in our mind, but this works really good as a calculation, like to run the stuff. So your p-value is the 2,000, you got your 1, you got your rate multiplied by the number of years right there. What I think is kind of cool about that is you can see this from a different perspective now, that what really happens is your rate, that 5% gets multiplied by the 7 and turns into 35%. So we end up multiplying 2,000 by 1 plus 35% or 1.35 and end up with that value. So you get to see a little bit more of a way to think about this. Instead of finding that percentage or interest at the end of 1 year, you can just multiply your percentage by the number of years and then do that calculation. By the way, a little bit later on, it's going to ask a question about why we have that 1. It must be like pages later, but they're going to ask about why they have that 1. And remember that it just goes back to this idea here that you always need to keep your main like starting value, your principal, that has to be included into all this. So as long as you've got that 1 in there, it maintains the $2,000. The 0.35 is going to create the $700 and automatically gets added together. Okay, 6. Let's see here. Sydney, she's going to owe money here, so she's not like actually saving money, but it's 8.25%. It's going to happen for 4 years. I think, her mom's involved in this one. So again, that's why it's a concept of simple interest and not what will be called later as compound. All right, the difference with this question and why we have it is we want you to see how using the formulas can allow you to find the original balance, the principal. So at the end of all of this, is the $11,305. We've got our rate, we've also got our time, which those two numbers I would go ahead and just multiply once you have it all written up, but you multiply them and it just looks like this. All right, you have your new value. You don't know the old value, but all of that can be simplified down to 1.33. So if you divide the 11,305 by the 1.33, you end up with $8,500, and that was your principal. By the way, that was all supposed to be worked out here, but sometimes you just set problems up and you just do them, so that's what the little arrow is for that part. But look, here's what's important about that question. You want to be able to use the formulas, not just have a conceptual idea of how the math is working, because when you need to backtrack and solve for something like the principal, or maybe have to solve for the rate, that's a tough one too. Having a formula that you can simplify and then just undo a couple operations is pretty helpful. All right, next we get to talk about compound interest. Compound interest versus the simple interest. This is what you would more likely see a bank doing. Simple interest is something that you would be doing with your buddy. And I mentioned that at the beginning, but I just want to reiterate that part. So this is going to be a more complicated calculation. It isn't impossible. Once you get used to it, it's pretty straightforward. Okay, here's the big phrase about compound interest. It's interest on interest. Okay, when you do simple interest, you just figure out what the interest would be for 1 year, and then you continue to add that number. But compound interest, it's going to take what you had as a balance, it's going to add interest onto it at the end of the first year, and then it's going to use that new value, that higher value, to calculate the interest for the next year. So you're technically creating interest on top of interest that was already on there. I'm not going to read through all this. You should have read all that, but it's going to ask this question, which I got a little bit confused because I didn't understand what was in the parentheses here, but it's going to ask you which one's going to result in more money. Is it going to be simple versus compound? It's going to be compound because you are getting interest on top of the interest. The simple, it's always the same amount of interest every time. But the interest on interest is going to start creating slightly larger amounts of money each year because you're using a higher balance to calculate your interest. What was the next one here? Oh yeah, this is always a cool question. Compound interest is good if you've got an investment. If you've got money in stocks, or if you've got money in, I don't know if you really get interest on stocks, but you know, if you have money in the bank, some sort of a savings account deal, you want compound interest because you're going to get a little bit more out of it. If you have a loan, like you borrowed money to buy a car, you would love it to be simple interest. Okay, the truth is it's a silly question because you are going to be doing compound interest. The banks aren't going to loan something out as simple and get less money back on it. But it's a good question as far as understanding that the difference between is. Okay, and now I'm going to throw one more thing out here because we don't really get to talk about it throughout the activity. But compound interest is what we call an exponential function. If you were to graph it, it gets sort of like a curve shape. At some point, it speeds up really fast in the increase. Simple interest is actually something that would be linear because you're always adding the same amount every year, like the $100 for Zach. All right, for the next several parts here, yeah, the next 2 pages, what we're going to be doing is developing the compound interest formula. So what I'm going to do here, because you should have already done the activity, what I'm going to do is just show you the compound interest formula. And I'm going to talk about some parts here. And then as we go through the activity, you can see which parts that we're actually trying to develop. Okay, so this is compound interest. You have your principal, which is still outside of parentheses. You've got the one that's going to maintain the principal. Okay, and here's your rate. You've seen this look a little bit different in the other formula, but you have a rate that gets divided by a number called n, and all of this gets raised to the ny power, where n is the same number that we have here, and then the y value is going to represent the number of years. All right, so this might be an awkward transition in the video, but you may have heard in the background my son was screaming, and apparently there were bugs on him, so I had to pause the video there. But I believe the spot where I left off was briefly talking about n. N is going to be a number that refers to the number of times that you compound in a year. And all that's going to be getting explained through this. But I want you to be able to see what all the different numbers or the variables are representing in that formula. And I'll try and keep coming back to that as we get through it. Okay, so the idea is that any bank is not going to calculate money just once a year at the very end of it. They're going to calculate it more often. So we pose this question first that might seem realistic because you get monthly statements from your bank. So they say, well, what if we want to do something that's called compounding monthly? Okay, and what they're going to do is take an interest rate that they have for the year. So they're saying 12% for the whole year, and this is out of conveniency. If they had a 12% interest for a year, that's the APR, and you want to figure out what the interest rate would be per month, then you would just divide that interest rate by 12 because there's 12 months in a year, which turns out to be 1%. So that number is chosen just out of conveniency. So you get a nice number like from the division, you get 1%. All right, let's see here. There's a girl, Rebecca. She's going to deposit $1,000 and she has this APR, and it's going to be, there's the key words right there. It's going to be compounded monthly. Okay, so if we're going to calculate the interest rate for a month, somewhere it's going to say that question. Let's see, it says, given that Rebecca earns 1% for the first month, calculate how much she will have in the account after that first month. There it was. Okay, so we take her principal balance, $1,000, and we're going to multiply it by 1 plus your rate times the number of times it's going to get compounded. Okay, we're going to be careful that this is only one time it's getting compounded because it's only 1 month that's passing here. So that looks a lot like your simple interest formula, but your t-value is not measured in years. It's just representing the number of like cycles that you compound. And sorry, that's the wrong phrasing. It's going to represent the number of time frames that corresponds to this rate. That one's a tricky one. Anyhow, when it multiplies, you get this. You get $10,010, nice rounded number there. Okay, so here's where it's going to get more interesting. At the end of the first month, using only the 1%, she has gained $10. Okay, for the next month, all of that is going to represent the starting balance. So that's going to be your p-value sitting in front of the parentheses, and that's going to get multiplied by the same thing we have up there. Notice I did simplify that just down to 1 plus 0.01. It could have also just been 1.01. Okay, so then we multiply there and we get this number, which has also gone up $10, but $10.10. This tiny bit difference in there. All right, so we're going to make a table to represent like a flow of this month by month. So original balance, end of the first month. Okay, that becomes the starting balance to figure out the balance at the end of 2 months. There it is, same number. Okay, so then you just take that number and you multiply it by 1.01, just this number. So new balance multiplied by the stuff in parentheses, and it gives you that. And you just keep multiplying by that number every month. So at the end of 5 months, this would be the balance that they get, right? So different than simple interest, because in simple interest, you would have only gained $10 a month. But we're starting to see they're gaining a little bit more. By the end of 5 months, they've actually got an extra $1.01 out of this. So it's not a big difference, but it's a little bit more. All right, this question, I referred to that earlier. Why do we use the 1? Like, why is that 1 in there? I don't think they're real specific on which one they were talking about, but it's that one, and that's because it maintains the previous balance and from the distribution and all that stuff I mentioned earlier. Question B, why does it make sense to use simple interest formula for each month? Because, oh, that's what it was. Because the way that we're approaching it here is we're calculating 1 month at a time. So you can take that previous balance and you can use simple interest just to calculate the next month. Okay, where that's not going to apply in a little bit is if you don't want to make a table or you don't want some redundancy in the calculator forever, but you just want to find out what something's worth in 10 years, right? We're going to end up branching away from like using the simple interest formula. But for right now, just moving like line by line, that's totally fine. Okay, so this is the part where we start developing the formula. We start getting close to this by looking at the numbers that we were doing. So a really cool thing here is that we did do the table. So you can start to see the pattern in the numbers, which was the multiplying by the 1.01 repetitively here. All right, so most of that should make sense here, that we had the 1 plus the 12% divided by 12, which was the 0.01, multiplied by the number of months, which in our case was only a 1. Treating it like the simple interest, there was only a 1 there. Okay, so that ends up just going this blank. And let's see here. This is going to represent, oh, where are we? Oh, so that is representing how you get the balance at the end of 1 month. Okay, now at the end of 2 months, you're going to take what you previously had calculated for the end of 1 month. So that's just this piece here, right? The principal times that stuff at the beginning, and you got your new number that then gets multiplied by those parentheses again. Okay, so this, with respect to the last problem, yeah, what was that amount? Was it $1,000? Yeah. Okay, so that would have been $1,000 multiplied by the 1.01 gives you the 1060, no, 1010, gives you the 1010. Then that multiplies by another 1.01, which gives you the 1,020 and 10 cents. Okay, but what we really want to notice is that there's this repetitive multiplication, that you have your principal and it keeps multiplying by the 1.01. So to simplify that, at the end of 2 years, we could have actually just called it this. Instead of writing all that, we could just say, look, it's the original principal multiplied by the 1.01 to the second power, because there's 2 times that it gets multiplied. And at the end of 3 years, you could actually just change the exponent to a 3, and it automatically applies the 3 multiplications of it. And if you want to do this for a full year, just raise it to the 12th power, right? Whatever you need. Okay, so that's what D and E are really going to talk about here. Notice, let's see here, the number of times that the interest has been compounded shows up in the exponent of the formula. So the number of times that we ended up multiplying by the 1.01. Okay, so for a whole year, that would need to be a 12, because we're doing this monthly, and there's 12 months in 1 year. If you did it for 2 years, it's going to be 24, because that's 12 times 2. Oh, by the way, you don't have to compound monthly. You can compound a different number of times a year, which is going to show up in just a little bit. Okay, I think you got that part, number of years. Okay, there's a bit of a jump here to get to the formula, because you're going to notice that the t-value sort of just drops out. Here's what we still have, though. We've got our principal, we got our 1 plus. You've got your APR divided by the 12 for the monthly compounding that we did, but there's no t-value. So I went ahead and wrote a note over here that, look, in our problem, t was the number 1, because we're calculating every month with it. So t was a 1, which really means that it didn't need to be there, right? Whatever you get when you divide here times 1 is still what you get. So you can just take the t-value out. Now we take a look at the exponent. The number of times that we compound per year, so if that was 12 times, you would need to multiply it by the number of years to make sure you account for all of the compounding that occurs. Sort of like this, if you want 2 years, you just need to make sure that it's a 24. In the end, look, you're not going to need to reproduce all the stuff that's up here. What we need to make sure is that you'll be able to use this formula with it. So we have a good idea of what P is. It's the principal. We know that this is our rate. We know that N is some number that refers to compounding. Right now, we only know just monthly. The Y value is going to represent the number of years that this goes on. Okay, previously mentioned, I said that the N value does not have to be a 12. There isn't a set rule that this is just a formula for compounding monthly. Okay, but if you do compound monthly, then the N value is the 12. It shows up here and there in the formula. One's where it divides your rate down, and the next where make sure that you account for it as many times as you need. Okay, but there's other ones here. You've got compounded weekly. Now, this isn't exactly right, but we assume that there'd be 52 weeks in a year, so you could just use 52 for that number. Compounded quarterly, That means you do this every 3 months. So we divide the year up into like 4 sets of 3 months, so 4 of them, and hence quarterly. So you'd have an end value of 4. You can even do daily. We use 365 for daily. Again, that one's not technically perfect if you know that information, but it's pretty close and it'll work fine for examples. Okay, then there's a whole bunch of other ones that are out there that are available, but these are the main ones that you'll see. There is one that is semi-annual. That one I was surprised was not on the list, but I'll add it. That just means twice a year or every 6 months. Okay, so twice a year. So the key thing is how many times in a year it happens, right? There are 2 halves of a year, so it's 2. Okay, there's some other ones out there like bi-monthly. If you never heard that, that means every other month. So that would happen 6 times in a year because it's every 2 months. So you'd have a 6 for that one. That one doesn't really get used much, but I'd go ahead and show it to you there. All right, so next we're gonna do a couple problems here where we just practice using the formula. We got Kyle who invested $12,000, that's the p-value, 4.5% APR compounded daily. You gotta look for those words there, compounded daily. So here's your formula all filled in. You got the 12,000, you got the 1 plus 0.045 over 365. That looks crazy, right? That you're dividing by that much. And it might even look even crazier here that we're gonna do 365 as an exponent, let alone 365 times 6, okay? But this is gonna turn out to be such a small number that when it gets raised to that really large power, it doesn't make too big of a difference. Okay, you're all. Now this is something that you'd wanna have a decent calculator for, but if you don't, I think I can show you like the order and how you want to do all the calculations. Where is it? Yeah, so obviously you can see on this one, it's pretty user-friendly to get everything typed in there. Hopefully I did type it in all correct. I had forgotten to do this problem earlier, so I'll just hope that I did it right. Okay, individual pieces though, you can figure out the exponents. Those are going to be integer numbers. They should be for the most part. So you can just remember that it's that number. The inside part, you could start with 0.045, divide that by 365. It's going to give you a really tiny number, right? At least have it calculated to scientific notation, but we'll add 1 onto that. Okay, so pretty much the same thing here, just with the 1s now in front of it. That gets raised to your power. Now, most calculators, even phone calculators, you should be able to choose your own exponent. So you take that answer and you raise it to the power that we already found. So that might make sense why I found that power first. Then that number, you multiply by your principal. And then, of course, I got that again. It's good if you have something like this, though, okay? You might not, but those are the steps individually, just in case. All right, 13, Maria, she's going to invest for 5 years at 3.15% interest compounded monthly, right there. Okay, so that means that all your ends, both of your ends are going to be 12s. You've got 5 up there by that 12. There's your rate, changed to decimal form. And like we saw a little bit earlier, this is the question where we want you to find the principal balance. Well, the neat thing here is that all of this is something you can calculate. And I just showed step by step how you can do that. So you could run all that calculation and it becomes a single number that when multiplied by p gives you the final result. So if you just divide 5,000 by the number that we found, it turns around to give you this answer. Now, as a little bit of a side note here, when I did this, I did it all in the calculator, so I kept building off of previous answers, which means that right here, it wasn't exactly 1.17. I think there might have been a 0 after that and then some more numbers. So you wouldn't think that a 0 and then some more numbers would make a big difference, but if you do round it to that spot, it turns out to be, I can show that part. We'll take the 5,000 divided by 1.17, and you actually get a different answer. It's different by about $1.90, I think it is. Okay, so as you do this, we'll be flexible if you're rounding off to maybe like 2 decimals, but it would be better if you keep it to about 4, if you can do that much. All right, final page here. What we really want to get to is understanding what is the annual percentage yield. But I think more important, like within the problem, is to understand something else that's happening as we change the number of times that we compound here. That does get addressed here in the table, but I think I'm going to highlight that a little bit more. Okay, we have a bunch of examples here that are only going to be like within a year. The difference in each of these is going to be the number of times that you compound. So the end value, if this will be annual, which is basically simple interest here, that would be 1. A simple interest if it only goes for a year, just to be absolutely correct in how I said that. Monthly means 12, weekly means 52, yeah, 365. You could even done like quarterly with 4 and so on. At the very end, hourly, 365 days times 24 hours in a day gives you this number here. Okay, but notice, these are all increasing. That's what we wanted to show you here is this, as the number for n becomes something larger, meaning that you compound more often, what happens to the values? So if you use this calculation, this is what 6%, by the way. Your y value is a 1, so it's really just n and n for those. These are all the values you get. And what you want to see is that as you go down the table, the numbers are getting bigger. All right, this is a difference of $1.68 here. But then when it goes up to this one, it looks like it's increasing by 12 cents. It's increasing by 3 cents, by 1 cent. So ponder that for a second here. The more times that we compound, the more we compound it, the bigger the return is going to be. However, the increase is less the more you compound. So it's always increasing, but it's less the more you compound, because we just went from 365 compoundings to 8,760 and it only increased it by 1 cent. Eventually, what these will do is they will level off. Ah, there it is right there. Okay, the more you compound, the more you get back, but it is going to start to level off. Now, just for kicks, I'm going to give you one formula here. I don't think you need to know that for anything in this, but for those of you who want to know, this little bitty formula here is what we call continuous compounding, and that's if you were going to compound an infinite number of times in a year. So even like not every second, but like every 1/10 of a second, and even less than that. All right, and E is a button on your calculators. Even your cell phone's going to have this one. All right, what do we got? We got $1,000. And there's actually like a button where you can just recall e to a power. Like it's not even just e, they'll have it with an exponent spot because this is actually so common. There's my percent. Our t here is our y value. That's going to be the number of years, so I don't do anything with that. All right, and then if you compare that to these guys, it's basically that number. This one actually rounded up to get to that answer, okay? But this would be the formula if we were doing what's called continuous compound. And it also tells you where we level off. We do level off at 84 cents. Okay. All right, so for our final piece here, we do see in the table above that the more times you compound, the more you actually are getting. All right, so that means that your interest rate as advertised, your APR is not really your final interest that you get. Okay, so there's this thing called annual percentage yield. Another way that you can look at this one is at the end of a year, at the end of 1 year, what percentage does it really look like? Now to do that, what you do, it's a real easy calculation except that it's built on other answers. You take what your actual increase was, it's called absolute increase, and we talked about that word before. So that means subtract the new balance and the old balance. Basically find your interest that you gained and then divide your interest by your starting amount. So it finds the percentage of your original amount. All right, so in the weekly row, we started with $1,000, and at the end, this is the amount of money that was gained. It was the difference between the balances. So if you divide that by 1,000, divided by its original amount, then you get this. So it actually feels like 6.18%. So just a little bit more than 6%, but it's still enough to make a difference. All right, and then 17, do the same thing for daily. Just take the similar values, divide it, and you're going to see that that one is it's basically the same thing, but still larger than our 6%. All right, and 18 is APR or APY larger. It's going to be the APY. The more times that you compound, getting interest on top of interest, you get back just a teeny bit more. So the answer, right? I might have answered it wrong. Is the APR or APY larger when interest is compounded more? I don't know why I wrote yes. The answer is APY.